Hello, welcome back to AE 2220 Dynamics. In this video, we're going to be starting chapter 1, which focuses on the kinematics of particles. Something I forgot to mention in the introduction is that we'll be using skeleton notes in this class. What that means is you'll have access to an incomplete copy or version of the notes that I'll be lecturing based on, and I'll be completing those notes during class. And I'll also be recording the lectures and then uploading those to YouTube and posting them on Canvas in case you ever want to go back and watch a video that you missed, or maybe you want a clarification on something. You'll have access to that as well. Okay, so we're going to start off with discussing what is known as rectilinear motion of particles. So a particle moving along a straight line is said to be in rectilinear motion. That straight line doesn't necessarily need to be in a particular direction. However, you could always define a coordinate system such that it's moving along one of your cardinal directions. We need two variables to describe this type of motion. The first variable we're going to need is time, which we'll represent using the variable t. And then we need some distance along that line. Some distance along the line, and we're going to call that x of t. So x is the distance or the displacement across that line, and it is a function of time. And from having time t and x of t, we can define everything needed to completely describe the motion of that particle, which includes the position, the velocity, and the acceleration. So at any time instant t, a particle in rectilinear motion occupies some position on a straight line. And we're going to go ahead and we're going to draw our straight line here. We'll say that we have some origin here, and then our particle is over here. We'll call that P. And we are measuring that position, x of t, from the origin to the current location of the particle. So in this case, to define the position of the particle, we need to do two things. First, we need to choose a fixed origin. So we need to choose a fixed origin. And then second, we need to choose a positive direction. A positive direction along the line. I'm going to move that A over a little. There we go. So we're going to along the line. So what that means is that we need to know where the origin is. That allows us to define x of t. And we need to know what direction is positive so we can tell whether the particle is in a negative or a positive position. And the motion of the particle will be known once its position is known for all time. Once we know the position, we can then go and compute things like velocity and acceleration. So if we know the position is a function of time, we'll know everything that we need to about that motion. Now, if you know the position at a single point in time, like t equals 5, then you don't have enough information in order to know the motion of the particle. In that case, you'd also need to know the velocity. And this is true in general of systems. It's not just true for rectilinear, but this is true in general. And that's because we will call the position and the velocity, these are what we call state variables. So you must know both of them in order to know the state of the system. However, if you know the position of the particle as a function of time for all time, then we know everything we need to know because we can use the position to compute the velocity. Okay. So let's consider a particle at position x at time t, and we're going to add a small displacement delta x over some time delta t. So let's go ahead and draw our line. Here's our line. Here is our origin. Here is the particle at time t. And then here is the particle at time t plus delta t. From our origin, we're going to measure the position of the particle at t. We said that's x. And then at a later time, it will have moved delta x. Okay, so then here we can define an average velocity. We'll say that our average velocity, the average velocity of the particle is defined as delta x over delta t. This will have units of meters per second, or maybe inches per second, or feet per second. We were generally working SI units in this class, so meters per second. Okay, let's let delta t go to 0, and then, well, we'll take a limit. So in the limit, as delta t goes to 0, this delta x over delta t. And one thing we forgot to add, because x has a direction associated with it, it should actually be a vector. And in this class, I'm going to use underlines to represent vector quantities. I won't be using an arrow over the top, but you are free to use that if that's what you'd like to do. Again, I'm going to use an underline here to represent vector quantities. So this delta x, that is actually a vector quantity. So if we take the limit of delta x over delta t, this is going to end up being equal to, as delta t goes to 0, this will be equal to dx vector over dt. So this is going to be the time derivative of that position. We'll call this x dot of t. Or we'll also call it v of t. And these are known as the instantaneous velocity, which is a function of time. That's why it's instantaneous versus before we just looked at the average velocity. So the dots here represent derivatives with respect to time. And you can see here that the velocity is also a vector quantity, meaning that it not only has a magnitude, but it also has a direction. Whereas something like, well, speed is just a scalar. It doesn't have a direction associated with it. It's a magnitude. The velocity is a vector. And the velocity describes the rate of change of position, and its magnitude is going to be known as the speed of the particle. Like I said, speed is a scalar. It's not a vector. Okay, let us now consider a change in the velocity delta v. And again, this should be a vector. So I'm adding an underline to the delta v over time delta t. And then what we'll find is that if we were to compute this delta v over delta t, we would find that this is the average acceleration in a particular direction with units of meters per second squared, or feet per second squared, we could say. It could also be inches per second squared. Again, generally we'll use SI units. We're again going to take the limit as delta t goes to 0, and doing so we'll take the limit as delta t goes to 0 of delta v vector over delta t. This is going to be equal to the derivative dv over dt, which is equal to d squared times d squared x dt squared, which we'll say is equal to x double dot under bar equal to a under bar t And this is the instantaneous acceleration, which is also a vector. So the double dot here represents a derivative, a second derivative with respect to time. So the acceleration is, we can show, is the second time derivative of the position, or the first time derivative of the velocity. So acceleration describes the rate of change of the velocity. And another expression that we can put down for our velocity is actually going to be A of t is equal to the velocity times dv over dx, which may pop up somewhere.